Welcome to Beyond the Headlines, the invisible power of academic research in America. Today we come together to celebrate 8 decades of a successful partnership between the federal government of the United States and both public and private universities. In today's seminar, you may hear many times about Vannevar Bush, but who is Vannevar Bush? He's the author of a 1945 landmark report that became known as Science, the Endless Frontier. Vannevar Bush was the vice president of the Massachusetts Institute of Technology, MIT, and later served as president of the Carnegie Institution for Science, an organization that funds and conducts scientific research. Among many accolades, he received the National Medal of Science in 1963 before the National Academy of Engineering elected its first members in 1965. From 1940 to 1948, Vannevar Bush served as chairman of the National Defense Research Committee, NDRC, which coordinates scientific research for military purposes during World War II.
I'm sure it would be somewhere
Among the many accomplishments of NDRC are radar developments, early research on atomic energy that led to the Manhattan Project, sonar and anti-submarine technologies, and numerous other achievements, including the development of insect repellents. Vannevar Bush's report laid the foundation for the post-war research system that led the United States' global leadership in science, technology, health, and defense. His landmark report argued that federally funded basic research at universities was essential for national progress and that the government should support science through competitive grants while university retained academic freedom. It always starts with FDR, a visionary leader whose New Deal policies fundamentally redefined the relationship between the federal government and the American public. On November 17, 1944, FDR requested recommendations from Bush regarding 4 major goals, 2 of which were: what can the government do now and in the future to aid research activities by public and private organizations? Can an effective program be proposed for discovering and developing scientific talent in American youth so that the continued future of scientific research in this country may be assured on a level comparable to what has been done during the war? By the time that Bush's landmark report was complete, FDR had passed, and Vice President Harry S. Truman became the president and implemented the recommendations. Science, the Endless Frontier, led to the creation of the National Science Foundation in 1950, expansion of NIH, DoD funding, and NASA. Another milestone in the last 8 decades of success that we celebrate today was the Bayh-Dole Act of 1908, allowing universities to retain patent rights on federally funded research, boosting tech transfer. This landmark legislation was the result of a bipartisan effort led by Democratic Senator Birch Bayh of Indiana and the Republican Senator Bob Dale of Kansas. Long live the partnership that propels the United States' global leadership in science, technology, health, and defense. Now, it's my pleasure to introduce the first keynote speaker of today's webinar, Professor Randy W. Schekman of the University of California, Berkeley, commonly known as Cal. In this photograph taken at the most recent annual meeting of the National Academy of Science, NAS, Randy is pictured on the right alongside his partner and colleague Sabiha Merchant, an accomplished scholar and the Howard Hughes Medical Institute HHMI investigator. On the left is NAS President Marcia McNabb. The Einstein Memorial, located at the NAS and open to the public, features a 4-ton bronze statue of Albert Einstein. In appreciation of Rand's generous contribution to the Academy, NAS presented him with a miniature version of the memorial, a little Einstein. One of the engraved quotations at the Albert Einstein Memorial is especially worth highlighting. As long as I have any choice in the matter, I shall live only in a country where civil liberty, tolerance, and equality of all citizens before the law prevail. Randy is a product of the University of California. After graduating from UCLA, Randy received his PhD from Stanford in 1975. He then crossed the Bay Bridge and moved a little bit north to join the faculty at the University of California, Berkeley. In 1981, he earned tenure and became associate professor, being promoted to professor in 1984. He has been a HHMI investigator since 1991 and received many accolades. Let me remind you of a question posed by FDR in 1944. Can an effective program be proposed for discovering and developing scientific talent in American youth? In 2013, Rand was awarded the Nobel Prize in Physiology or Medicine. Here's a brief clip of Randy explaining his research in his own words.
The work in my laboratory probed the molecular basis of protein secretion in baker's yeast. We had no notion of any practical application of this work.
Without much further ado, let me turn the virtual podium over to Berkeley, California. Please join me in warmly welcoming Randy Schekman and express our deep appreciation for his participation in today's seminar. Randy, the floor is yours.
Thank you very much, Walter, for your generous remarks. In considering the invisible power of academic scientific research in America, I wish to address two specific triumphs of recent biomedical science, as well as the perils we now face with a government bent on attacking the foundations of our success. Those of us who study the natural world are often called on to justify our work in terms of practical applications. Naturally, governments invest in the pursuit of discovery with the expectation that society will benefit with technological and medical advances to improve our lives and to ease the burden of disease. But for many of us, there is a deeper meaning to our pursuit of the truth of the natural world. Our natural curiosity about the world, indeed the universe in which we live, drives us to explore well beyond our need to feed, heal, and reproduce the species. We have evolved beyond all life forms on Earth, and likely in most of the universe, as we seek to understand ourselves in the fundamental principles of nature. The examples of basic science driven by curiosity are numerous and must be heralded for all to appreciate the intrinsic value of knowledge. My favorite is the understanding of an arms race in which bacteria and their viruses fight it out to survive in the biosphere. Did you know that the viruses that infect bacteria are by far the most numerous biological objects on Earth? Every milliliter of seawater has 1 million bacterial cells and 10 million bacterial virus particles. These mortal enemies have been doing battle for the past 3 billion years. During this evolution, bacteria have found a way to sniff out invading viruses by producing a small piece of RNA that matches a viral DNA sequence not found in the bacterial chromosome. This piece of RNA comes associated with a bacterial enzyme that chews on the foreign DNA, breaking it into non-infectious pieces. Viruses counter this offense by evolving new sequences not detected by this RNA, but then bacteria evolve to produce new RNAs and so on. Now, why should we care about this seemingly arcane bit of microbial natural history? Well, these discoveries have led to the current revolution in genome editing with the prospect to cure human genetic disease. In fact, just in the past 2 years, the application of this technology has made it possible to cure patients with sickle cell anemia, a genetic disorder of the blood that afflicts millions of Africans and their descendants around the world. This is only the first of a new wave of treatments tailored to cure genetic disease and to advance biotechnological innovation in agriculture. Breakthroughs in the sciences require resources that can only come from investments provided by governments, venture capital, and philanthropy. As Walter said in his introduction, in the United States, government funding of basic research started after World War II with a transformative report, Science, Endless Frontiers, written by Vannevar Bush, the science advisor to Presidents Roosevelt and Truman. He wrote, quote, "Scientific progress on a broad front result from the free play of free intellects working on subjects of their own choice in the manner dictated by their curiosity for exploration of the unknown. Freedom of inquiry must be preserved under any plan for government support of science," unquote. Opportunities for education in the US exploded in the 1960s. The race to space, initiated by Eisenhower and Kennedy, led to a substantial increase in federal support of science and science education. This investment nourished generations of American and immigrant scholars that made the US the world-leading powerhouse of 20th century science and technology. The lessons learned from this transformation have spread around the globe, with 21st century leading economies, China foremost among them, rising to match and in some ways exceed the pace set by the US. I'd like to share with you another example of how the attraction of American science served to raise a young woman from poverty to the heights of achievement with a key discovery that saved millions of lives in the SARS-CoV-2 pandemic. This is the story of Katalin Karikó, a Hungarian emigre who made the breakthrough discovery that led to the development of mRNA vaccine that so many of you have taken to protect against coronavirus infection. Katalin grew up in a home without running water, a refrigerator, or television, but with an aspiration to rise above that with an education at the University of Szeged and a postgraduate degree in biomedical science. Trapped behind the Iron Curtain, she sought refuge in the West and escaped with her husband and young daughter and a teddy bear stuffed with cash she collected from the black market sale of her car. She landed in the US and began a vagabond journey through various academic institutions until she landed a non-tenure track position at the University of Pennsylvania. There she hoped to realize her dream of a therapeutic application of mRNA, the message copied from genes housed in the nucleus of our cells. mRNAs carry a copy blueprint needed to construct all the protein molecules cells need for life. The plan was to inject an mRNA that would allow cells to produce a protein of clinical importance in treating disease. The problem is that mRNA molecules injected into an animal elicit an inflammatory response that makes them toxic and useless as a therapy. After years of struggle, she failed to gain acceptance and funding for her idea and was dismissed from the university with little prospect of employment. Fortunately, a sympathetic colleague at Penn, Drew Weissman, gave Catalin a second chance and a lab bench and a collaboration that finally overcame the problem of mRNA toxicity. The team found that some RNA molecules, those that have a variety of chemical modifications, manage to evade the immune system and are safe to inject into an experimental animal. By a trial and error test of the various chemical modifications, Herrico and Weissman discovered that one specific molecular change was enough to hide mRNA from the immune system and allow mRNA molecules to be injected for potential therapeutic application. Despite what we now appreciate as a revolutionary discovery, her work was rejected by the most so-called prestigious journals, but was instead published in the Journal of a Scientific Society. Seeking an opportunity to apply her discovery, Catalin returned to Europe to join a fledgling biotech company that at the time didn't even have a website. In collaboration with two Turkish immigrants to Germany who started the company BioNTech, and with financial support from Pfizer, the team launched the vaccine simultaneous to the American effort at Moderna, and the rest is history. In the time just after the launch of the vaccine, Herrico's role was finally recognized, and she has been celebrated, along with Weissman, around the world with dozens of major biomedical prizes, including the Nobel Prize. I had the pleasure of introducing Catalin at a drug discovery symposium, and in the Q&A after her talk, I asked how she dealt with all the adversity she faced in her life and in gaining acceptance of her ideas. Catalin remained upbeat throughout and was sustained by the courage of her convictions. In a response that I shall never forget, she said that after all, quote, I had my own lab bench and was in the United States of America. With all that we have faced in the xenophobic reaction to immigrants in this country, her courage and the simple confidence of the statement, I had my own lab bench and was in the United States of America, must resonate with many of you listening today. Catalin's experience as an immigrant to the US is not uncommon. Among members elected to the prestigious US National Academy of Sciences, about 30% came from abroad and remained to build successful careers in the nurturing environment of the American scientific community. Despite over 80 years of progress that led from the foundational report of Vannevar Bush, just a few months into the current presidential term, the infrastructure that supports science in this country faces an existential crisis. We are now challenged by an increasing antagonism to science and the scientific method, even to the point of ignoring the overwhelming evidence of a role for fossil fuels in climate change and a rejection of the success of the mRNA vaccines and the antiretroviral medications that have reversed the certain death sentence of an HIV infection. The current Secretary of Health and Human Services, who is neither a scientist nor a physician, has embraced the fringe views of vaccine and HIV/AIDS skeptics and has recommended canceling NIH grants supporting infectious disease research. He's fired all the members of the CDC committee charged with vaccine policy and replaced them with other fringe vaccine skeptics. Academic institutions where most of the basic science is conducted are under attack based on false claims of anti-Semitism and a supposedly unbalanced application of civil rights. Universities and research institutes have been directed to accept grants with an unsustainable low level of indirect cost, a restriction that has not been imposed on other government support for agencies such as those that support aerospace and defense industries. The NSF is being evicted from its headquarters. The director of the OMB has publicly expressed the view that science can be supported only insofar as it is consistent with fundamentalist Christian principles. If Congress proceeds with the current budget, FY26 will see a 50% decrease for the NSF and a 40% decrease for the NIH. We face a sea change in government support that has shocked our colleagues around the world, some of whom have offered a lifeline, not unlike the Marshall Plan after World War II. Science will continue to advance around the world, even as we take a back seat in adjusting to a new reality. Our place may be taken by those countries such as China, where an enormous investment in basic science continues to grow as our support dwindles. It is now up to our leaders of the scientific community to speak up more forcefully in support of science. This message must be taken beyond Washington to all corners of this country, as Bruce Alberts did in support of improved standards of science education when he served as the president of the National Academy. We have a powerful message to deliver that an investment in basic science pays enormous dividends in improved health outcomes and technological development. We need the next generation of scientific leadership to show that America can still lead the way. Thank you.
Thank you very much, Randy. Very powerful introductory remarks. I know that I have many questions, but we're going to hold the questions after Charles Rice. Okay, let me introduce Charles Rice. Our next keynote speaker, Dr. Charles M. Rice, also exemplifies the success of FDR's vision for discovering and developing scientific talent in American youth. He is also a proud product of the University of California system. Born in Sacramento, just about 15 miles from where I am speaking, Charlie earned his degree in zoology from the University of California, Davis in 1974. His path to becoming one of the world's most accomplished virologists began to take shape when he entered the PhD program at Caltech.
At the time that I graduated from Davis, I thought I was going to be a developmental biologist. I'd worked here on sort of sea urchin development, and when I sort of ended up at Caltech, the lab that I wanted to do my thesis work in didn't have room, so I got plopped in a virology lab, and that's really sort of the genesis of how I got interested in viruses.
From 1986 to 2000, Charlie served as a faculty member at Washington University in St. Louis. Today, he's a professor of virology at the Rockefeller University. He also holds adjunct appointments at both Cornell University and Washington University School of Medicine. In 2020, Dr. Rice was awarded the Nobel Prize in Physiology or Medicine for his groundbreaking discovery related to the hepatitis C virus. Now, let me turn the virtual podium over to New York City. Please join me in welcoming Dr. Charles Rice and expressing our sincere appreciation for his participation in today's webinar. Charlie, the floor is yours.
Thank you, Walter. It's really sort of a pleasure to be here, and thank you for sort of organizing this webinar. It's always impossible to follow Randy because he basically covers all the bases. And what I thought I would do, just to sort of emphasize, the importance of curiosity-driven investigation, is to sort of give a personal trajectory of sort of my career. And as you mentioned, Walter, I was an undergraduate at UC Davis, sort of on track to maybe becoming a vet. Davis also has a great vet school. And there was a biology course, introductory biology course that was taught, which really got me excited about science. And as I sort of mentioned in those remarks that you projected, what really turned me on was the prospect of understanding early development using the sea urchin as a model. And, you can mix sea urchin sperm and eggs together and, basically watch development unfold. But, sea urchins are not, sort of probably the kind of funding which, is going to yield immediate, sort of translational applications for improving human health. So, I ended up really excited about research and arrived at Caltech. And as I said in the clip, I ended up in a virology lab rather than the sea urchin lab that I was targeted for. And this virology lab was studying sort of new animal viruses that were enveloped. These are positive strand viruses like SARS-CoV-2. And but these two viruses were, probably again not all that sort of important in terms of public health. One of them was Symbis virus, which was isolated in Egypt around Cairo in 1952. And the other one was the vaccine strain of yellow fever, which Max Tyler had developed as a live attenuated viral vaccine that basically it's a different group of viruses that this is the prototype virus of, but basically this vaccine is amazing. It's one-shot lifelong protection, but why do you really need to study it? But, basically the NIH and NSF, provided the resources to be able to sort of study these things just as sort of curiosity-driven exploration. And, when I took my first faculty position at Washington University, we continued to study Symbis and yellow fever. It was work that could be, sort of funded by the government, even though it wasn't going to necessarily lead to a cure of an important disease. So you'd say this was kind of low translational potential, but we were curious about how these viruses replicated and spent a lot of time working on yellow fever, for example. And then in 1989, the agent that was responsible for non-A, non-B hepatitis was identified by Michael Houghton and his colleagues and coined hepatitis C virus. And this is a virus that was quite widespread, sort of more than 100 million people that were chronically infected with this virus, that this chronic infection was associated with the development of inflammation in the liver, leading to cirrhosis and hepatocellular carcinoma. And, this was a difficult virus to tackle, but we were interested in working on it because it was really very similar to yellow fever, where we had this experience of sort of studying a related virus so that we could actually begin to work on hepatitis C, having that sort of knowledge. And this was a very long road. We were not able to, sort of publish papers in prestigious journals because, the breakthroughs were few and far between. And it took I won't go through the trials and tribulations, but it took 15 years before we actually had systems in the laboratory to study this virus that were really poised to help develop sort of new treatments for hepatitis C. So that was, 2005. And then it took another 10 years beyond that in biotech and pharma to develop the compounds that we have today, which can cure more than 99% of those people that are treated with one pill a day for 2 or 3 months. So really, quite remarkable. And whatever sort of small role that I and my colleagues played in this, there were many people around the world studying this virus, really was a product of these kind of random encounters sort of early in a career, which really sort of shaped and provided the base to make a contribution. And I think if we don't sustain that, it's going to be very bad for, science and public health. And Randy, sort of gave a couple of just fantastic examples of how, sort of basic curiosity-driven science really can lead to amazing breakthroughs. And I really hope that the United States can continue to take a lead there, but we are in a very difficult situation now, particularly in the infectious disease space. So maybe I'll stop with that and just say that this is important. And again, thank Walter for sort of organizing this session.
Thank you very much, Charlie. So now we are going briefly to a set of questions and the answers, and then we move on and come back because we have a long program and different aspects of the issue to be covered today. Like Randy eloquently mentioned about the attack on the system and how important it is for us to speak now. So let me see if one of the designated questionnaires would have a question for either of the two speakers. Let me see here if one of them is available. I sent them a direct chat, but I didn't hear from them. Jawid Kalim is with the LA Times. I'm wondering if Jawid has any questions. Jawid?
Hi, yes, thank you for having me join. And Randy and Charles, really good to hear your remarks. I think one thing that stood out to me is I'm wondering if you have any thoughts on ways that researchers and universities can better communicate the work they do to the public. I'll give one example, of course, the indirect cost issue that's described as overhead by the federal government. But those of us or you who work in the arena know that that's much more than just administrative costs. It's an integral part of the operation. But I'm wondering, it does seem there's a public relations aspect here. How can the job better be done of communicating the work that you do and that federal and university relationship?
Well, I can follow with just some brief comments. I mean, people do speak out, but we don't have a voice. We need a voice. We need members of the leadership of the science community to take the opportunity to speak out in support of science. We have not had that for a long time. We need forums where these discussions can be voiced to reach more than those who simply read the New York Times and the Washington Post. We need members of the National Academy in all 50 states to have access to their local press, to speak out on these issues so that people who aren't in the mainstream of news sources have access to the information that we hold, but are sharing inadequately.
Yeah, I agree, but I think there's, sort of another layer that we need as well, where, sort of members of the community that, support science but are not scientists can really sort of play a role, because I think, we can be seen as, sort of entities that are people that are, it's kind of self-serving. We're scientists, we like science, we want to promote science. But I think if we have, sort of more people in the public sector that have really sort of benefited from science and some of these amazing sort of breakthroughs that have been made in science, their ability to connect with other people may be, something that will be beneficial in terms of getting the news out.
Excellent question. Is Tyler, do you have a question, Tyler, from NBC News? Is Tyler there? If not, I'll come to Tyler next. And now I'd like to, yes, Tyler?
Oh, yep. Hi. Sorry.
Yeah, go ahead.
Hi, thank you. Yeah, I was also wondering if you could also just speak to, there's been a lot of discussion about the brain drain in America and what it means if research shifts to another country, if that's even possible, or if that's something that you don't see, something of what I understand from history, returning to when Germany was the place to go a century ago. And also, I guess related to that, how do you advise sort of PhD candidates, grad students, people who are in the pipeline to become scientists and who may be looking for full-time work or a place to study?
Well, I can pick up on that on those two questions. The first is the reverse brain drain is happening. The Chinese scholars who have trained in the US for their PhD or postdoctoral work now have many more attractive options to return to China, even though I know from my own experience that many of them would prefer to stay in the US. But the restrictions, not only on funding, but the prejudice that they're experiencing, even well-established Chinese American scholars, the prejudice that they are experiencing is so antagonistic to their basic science work that many of them are considering and have returned to China, where hundreds of new universities are opening up with enormous funding. And even our European friends are pulling out all the stops to create opportunities to sustain this, what I referred to in my talk as a version of what happened after World War II with the help that we provided to Europe. Now, for PhD students or aspiring young scientists, I still feel, and I think I would not have changed my own career path, even given this restriction. There are some who are so committed to science and to understanding the natural world that they will continue to press ahead even with the adversity that they face. I have two PhD students who are just graduating this year who have obtained postdoctoral positions in the US, and I expect them to do very well, but it's going to be much more difficult. And I think this is going to particularly affect those students who came from abroad to make their studies and their career possibly in the US. We will lose a generation of those scholars.
Thank you very much, Brandy, for taking that question. We are going to show a little short video here, another presentation recorded at the end of this video. We are going to have the president of the National Academy of Science, Dr. Marcia McNabb.
Hi, I'm David Julius. I'm here with my friend and colleague, David Clapham. We're here in Normandy, France, visiting the World War II memorials and paying our respects to those who sacrificed here. But we're also here because Walter Leal has asked us to say a few words about the importance of basic biomedical research to society. And he asked us to either tell a personal story or some insights that we've had from our years as either clinician scientists or scientists. And I'll start off by telling a brief personal story. And that has to do with my father, who was diagnosed with metastatic melanoma when he was about 60 years old. This is some years ago in the 1990s. And there was not much hope for him, but he was enrolled in an experimental trial at the National Cancer Institute, at the National Institutes of Health. It was really one of the first trials to explore the ability of our own immune system to fight cancer. And really help to shape the way in which we think about that concept of immunotherapy. And his life was basically saved by this clinical trial. He lived another 25 years disease-free by work from Steve Rosenberg and his colleagues, who figured out how to stimulate his own immune system to eradicate the cancer that he had. Like many things that happen in medicine, this is really using basic knowledge of immunology and of basic science, basic cell biology, to understand how that can be parlayed into improving people's health.
Yeah, and just to add a few words, it's my own background. I started off in electrical engineering, then went into MD, PhD program, did medicine. But as I went through medicine, I began to realize how limited we were in our options for treating people, and so many people that we couldn't help. And so continuing in science, I think science is the way to really be able to cure, treat, reduce suffering for people. And if you think of what has saved the greatest number of lives in history, It is no doubt that penicillin and vaccines have saved more people than anything in the past. Vaccines are just the beginning, because now in the future we can hopefully save things like, or prevent things like neurologic diseases. My own son died of a inherited neurologic disease at age 9. I would love to see that we can treat such things in the future, and the only way to do that is to understand what the diseases, how the diseases work, and then how we can fix it so that they're healthy again. And we both feel strongly that science is the way you get to curing, solving disease, and reducing suffering.
Mm-hmm. We have to understand how things work to understand how they go wrong, and until you do that, it's just random shots on target. There's no rational way to cure disease unless we do the basic research that tells us how the human body works and how it goes awry when there's disease. Thank you, Walter, for including us in this webinar, and thank you for reaching out to all of us to try and make this important connection between science and society, which is more critical now than ever.
Thank you.
Thank you very much. So now Randy is smile because he was a student in his lab. So let's move now to the next keynote speaker of the day, Dr. Marcia McNatt. She's the president of the National Academy of Science and is serving for second term. And I would invite her to share the podium and give some introductory remarks.
Yeah, thank you so much, Walter, and thank you for allowing me to speak to this distinguished group. I agree with basically all the statements that my illustrious colleagues have made, and I'm, very honored to be here with so many Nobel laureates. Just a few thoughts. One of the biggest issues we face is that this administration has been very what would be the right word, clever in providing context for why they're making the decisions that they are, that actually go against what all of our experience is. Let me give you an example. The administration is very convinced that we need the very best people in science. And gosh, wouldn't it be nice if more Americans, more bright Americans, saw science in their future? But then they cut by a factor of 2 the NSF graduate research fellowships. Why do you cut in half opportunities for the brightest Americans to go to graduate school when your goal is to get more Americans involved in science? Another example, which Randy brought up, is our head of HHS wants to make America healthy again. But yet he is appointing to this vaccine panel skeptics who are looking for scientifically refuted reasons not to provide vaccines to everyone who needs them. And then another issue that they use to justify slashing research budgets is they say that the US is not getting as much bang for its buck as it used to, and then somehow equates that with we're funding the wrong science, which is, I think for any scientist will know that there is very little connection between a politically appointed person dictating what science should be done and what science breakthroughs will happen. We know that so many breakthroughs happen through serendipity, through random chance, the idea that there could be some way to only fund the half of science that is going to give breakthroughs and not fund the half of science that is going to lead to dead ends or perhaps, a discovery in a completely different area that wasn't anticipated when the experiment was done. So all of these are problems. I've heard many scientists, including statements we put out from the Academy, speak up in favor of what science knows to be the truth. Science knows it to be the truth that American science is great when we attract the very best and brightest from anywhere in the world here. But this administration is somehow equating bringing the best and brightest to America somehow with their illegal immigration crusade to throw people out of the country who shouldn't be here, when the scientists who come here legally. And as others have said, many have chosen to stay. They are more than a quarter of our members of the National Academy, all of whom became American citizens before they were elected. So they're not just here short term, they're here full time. And it's a very similar portion for the number of our Nobel Prizes that were won by first generation immigrants to this country. I think if you went to any of these leaders in Washington and said, would the Washington Commanders be a really good football team if they only recruited from the District of Columbia? I think they would all say no. We have to recruit wherever talent is. But yet, why is that true for sports when it's not true for science? Well, of course, it is true for science as well. And that's why we have to attract the best and brightest. There are two problems, though, with getting our word out. First is one that Charles already brought up, and that is it comes across as self-serving when scientists talk about the importance of funding science, because after all, science funding, although we're all in it not for ourselves, we're in it because we actually wanted to help people. We wanted to make the world a better place. But nevertheless, it will come across as us being concerned about our own salaries, our own labs, our students, our postdocs, and therefore not being treated the same way it would as when the beneficiaries of science speak up. I was so pleased to see an open letter that was put out by quite a large number of leaders in industry talking about shutting down the innovation pipeline by cutting funding to research. Those are the people we need to speak up. The farmers who point to their fields and say, I'm producing more bushels of crop at less money with less environmental impact and lower cost to consumers because of science. Or the mother who says, my baby would not be alive today were it not for science. These are the voices we need to get out there. Some of the problems with trying to get non-scientists to speak up in favor of science is that, frankly, this administration is dropping bombs on everyone. Look at all the people who are losing their medical coverage, or small business owners who aren't able to make ends meet because of tariffs, making cost of goods more expensive for them, or for victims of natural disasters who suddenly find out that the government's not going to be there to help them. And in particular, the government is cutting back its funding on the things that are most prospective, making communities more resilient to future disasters, to climate change, making disease surveillance systems operable so that we can see a pandemic coming and take immediate steps to mitigate its impact and to find a cure for the problem. These are the forward-looking things that just don't seem to be on this administration's agenda. And in addition to the fact that people are overwhelmed with these other things, it's really hard to imagine how they're going to stand up for science when they're worried about, will I be able to make my rent payment? Will I be able to buy food for my children? And yet we all know as scientists that we're going to be right in the end. We're going to be right in the end. This nation, our citizens, Americans, are going to suffer from these cuts to science. It will mean that we will not have the same new industries that are nucleated in the US that create better jobs for people. We know that we are not going to be ready as we were for COVID to turn out new solutions to health problems quickly. It's going to be a reduction in our environmental quality. And, you know, we talk about how much the government has taken down all these climate websites, how they've cut all funding for climate science. And they say that because they call science in climate science ideological. And yet, what could be more ideological than claiming that climate change isn't happening, but then wanting to buy or conquer Greenland? Who can possibly believe that the president doesn't think that climate change is happening if he wants Greenland? So I'll just leave it there and just say I think we have a huge challenge in front of us. I've been on many of these conversations. Often we're just speaking to the choir, and we need to figure out how we break out of that mold. Thank you.
Thank you very much, President McNatt. I want to quote one of two quotes from this press release with the letters of 100 CEOs. One said, Jeremy Levin, "This is not just a funding cut. It is an attack on the green engine of American innovation, a pillar that has powered our nation's health, security, and economic leadership for generations." A second one, I'm not going to read the whole quote because it's long. Paul Hastings completed by saying, "The American strategic asset has relied on an ecosystem of diverse talent from all over the world, resulting in a brain gain at our universities and ultimately at our companies. Now we will face a brain drain and hand over all our strategic assets to other nations, including China." So well said. So let me take a couple of questions. And this is a one-person operation. I have been doing everything, but I was very glad that one graduate student volunteer to look at the chat, especially the YouTube for me. Her name is Julisa Chavana. So I'm going to ask Julisa if there is any question there. And before she does that, I'm going to ask whether Julisa can tell us what her research is and how useful is to society. Julisa.
Hi, everyone. As Walter mentioned, my name is Julissa Chavana. I am an organic chemistry PhD student. I am part of the Mascal lab, and our lab focuses on industrially relevant synthetic organic chemistry. We have 3 different umbrellas: medicinal chemistry, sustainability chemistry, and fundamental chemistry. And more specifically, my research project falls under fundamental chemistry, also known more specifically as supramolecular chemistry, which is known as chemistry beyond the molecule, or also known as host-guest chemistry, which basically imitates a biological phenomenon, such as substrates binding to enzymes. And although I'm more focused specifically on capturing ions, there's room for supramolecular chemistry in controlling transport and storage for application in solar cells and fuel cells, extracting radioactive elements without disrupting other ions in our environment. And in addition to that, there's also room to develop targeted drug delivery systems. So those are just some ways that my personal research is relevant here in society.
Thank you. Any questions, any comments from YouTube or from on the chat that you want to highlight?
I am not seeing any questions, but I thought I should mention that someone mentioned potentially collaborating with film companies to basically share compelling stories of how research is important, especially since communication is obviously important in situations like these.
Thank you. So I'm going to open for questions and a little bit of debate before we move to the next segment. Randy, looks like you have some questions or some additional comments. Randy, if you unmute, please.
I appreciate the comments that Marcia made, and others said that maybe scientists aren't the best people to deliver these comments, but explaining what overhead means requires a scientist who has experience with how these functions are served. And if you ask someone in the public to explain that, you wouldn't get a very effective answer. So scientists do have a role, but perhaps not the exclusive role in communicating the value of science.
Any other comments? Another question that comes often is if there is no funding, why the universities do not use the endowment? I asked this question to president of the Arizona State University, and he answered the question for us.
So first, let me say that we've only had 80 years of intensive U.S. government support of academic science. I mean, prior to that, in 1939, there was $100 million, $150 million total in 1939 of federal support for research, and most of that was medical and agriculture. In fact, the vast bulk was agricultural. And so obviously then during the war, the model of the universities being called to national service was put in place at hyperscale, unbelievable outcomes, unbelievable scale. And then after the war, Vannevar Bush puts together this notion and says, okay, well, let's just keep this going. Let's keep it rolling. Let's call the universities to help. And it outlined this in Science, the Endless Frontier: national security, economic security, health security, all those things. And so if we just keep this model going of giving universities money, they'll do this science that will lay the foundation, and all these great things will happen. So then if the federal government changes its strategy and doesn't want to fund basic science in that same way going forward, so then the question is, well, why can't the universities use their endowments for these things? And the question is an obvious one from an outsider looking in, and it's very, very complicated. I can tell you that the answer is that of all of the endowment-based gifts that universities have within their endowments, 95 to 98% of them are for a specific purpose. I'm giving you this money to support the West Wing of the library's collection on Japanese American politics. I'm giving you this endowment to support 5 graduate students in chemistry. I'm giving you this endowment for the new library operations in the business school. So at a place like ASU, this is in the thousands and thousands and thousands of individual projects. And so the amount of programmable endowment at every university is tiny. And then on top of that, endowments themselves are not well understood because they are money invested in investments, largely the stock market, the way your retirement funds are. And it runs very much like a retirement fund in the sense that you can only spend a certain amount of the endowment, usually 4.5%, give or take. And then that then allows the rest of the endowment to continue to grow so that the endowment can always produce 4.5% for use. And so let's say you then therefore have let's say you have a $1 billion endowment. Well, 10% of 1 billion to spend is 100 million, 5% is 50 million, 4.5% is $45 million. So you have $1 billion endowment, you only have $45 million to spend. And of the $45 million that you have to spend, 95% of that, so you can run the numbers yourself, are directed to specific things, some of which might be related to research, most of which are not related to research, some of which are related to faculty, some of which are related to students, some of which are related to the crew team or to the coaching staff of the basketball team. All these things are endowed throughout the institution. So at the end of the day, you might have a few $1 million per every $1 billion of endowment for new discretionary research.
Thank you very much. Let me stop that in here. Stop sharing. All right, so that's a statement about the endowment, and there are many questions that the people asking about the overhead. It's a very simple explanation that even people within the university sometimes don't understand. Why do you accept a grant from the Gates Foundation with 15% and the federal government has to pay 60%? So that's very legitimate questions, and we have to admit that we're not doing a good job on that. Jaweed, do you have a question specific for this cycle now?
I think I have an extension of the endowment question. The other area is where members of the public or even the political leadership right now say, go to the private groups for your funding. And this is happening on a much smaller scale right now. Harvard the other week established a $40 million bioscience lab funded by a Turkish private equity fund, but that's 40 million compared to the billions and tens of billions that are at stake. But I'm curious. I've also heard with the private model that generating profit in the product very fast is the key versus the long-term basic research at universities. I'm just curious, where is that conversation going right now, if anywhere?
So let me engage in here one person. Maybe Randy wants to address that question.
Well,
No?
I would just say to Joey that the same thing that applied to the endowments in universities applies to private donations to universities. They are often earmarked. I have the pleasure of serving the Sergey Brin Family Foundation to organize a worldwide program on Parkinson's disease. It's a valuable contribution he's made, but it's earmarked for Parkinson's disease and not other things. So billionaires also have specific interests, and they aren't necessarily interested in giving unrestricted funds.
Very good. So Jean Hildebrand here with us is a Regents Professor of the University of Arizona, is also a member of the Council of the National Academy of Science. John, on the issue of the overhead, do you have any simple explanation for the public or something else that you'd like to address?
Yeah, well, it's a terribly important issue that really we need to explain, among other things, that it wouldn't be fair to use student tuition to pay for the work that's done in research labs as opposed to what's needed to teach them in classes. We need the tuition money, that's the other main income stream for a university, to run the educational mission of the university. So when people blithely say, well, just use student tuition to pay for the overhead, I don't think that would be fair to students. And we have to tell that story clearly. While I have a chance to speak here, I'll just say, in my role as the International Secretary of the National Academy of Sciences, I've had the kind of heartbreaking experience in the last 5 months of hearing from colleagues in other academies around the world who say that they're solid with us, they sympathize deeply, but we're not going to be reliable partners anymore because they see the United States as just abandoning its responsibility and its ambition to be major contributors to science. I hope it won't really be a matter of disengaging with us, but I can understand the perception that we as a country and a scientific enterprise will not be reliable partners anymore.
Thank you, John. And it looks like Marcia McNutt has something on that one.
Yeah, no, I just wanted to chime in on this indirect cost issue. So I talked to the people in my finance office about the indirect costs that are supported by foundations versus the federal government. They told me that private foundation grants come with so many fewer strings and trip bars that they are much less expensive to actually administer in terms of regulatory compliance than the research grants from the federal government. Nevertheless, the Academy still finds the money out of its endowment to make up the difference in indirect cost base between what the foundations pay versus what the government pays. And I think many other organizations do that as well. So this is a draw from our endowment in order to fund it. And as I said in my State of the Science address last year, right now at universities, private foundations fund almost as much basic research as the federal government. There's only a couple percentage points difference. The problem is that private foundations simply don't have the capacity to make up for this loss, this huge loss in federal funding. It's just not going to happen.
Now, there's one person that we know that has an experience of these 8 decades of support of the federal government. So let's stop for a minute to listen to what the Thorsten Weiss, another Nobel laureate, has to say about this partnership.
I wanted to say a few words about the trust that has existed between the science community and the support from the federal government, and in my case, through NIH. And I think it turned out that with science being supported from in different states all over the country, the scientists came to learn to know the representative Congress members, and they talked to the members of Congress about their science, and they learned to know each other, and this became like a community of both scientists and people in Congress who shared the interest and were involved in the progress made in trying to cure different illnesses and development of science as a whole. And I think that initially, NIH, any discovery you made in the laboratory and you had patent on, that belonged to NIH. But then after about 30 years, in the 1930s or so, there were two senators, and I've forgotten their names, were able to change the law so that Congress, in fact, gave the authority and ownership of the patent to the universities and to the scientists who made the discoveries. And that has been a crucial step in the development of research in America and creation of new companies for various purposes in the drug industry and elsewhere. And I think that interaction between the scientists and the members of Congress was a very productive and made us feel part of a community in a sense that, and that has disappeared. And I don't know really why it has disappeared, but it seemed as if we have, I don't know any person in Congress, and there's no discussions anymore really between members of Congress and the scientists. So that community that was a base for, and why Congress over the years have always been more generous than most administration in supporting science, usually increase the budget to some extent. And I think that is a change that I regret having happened, because it perhaps also meant that the science community has sort of lost its contact with the general public. So they look upon scientists as some people in the ivory tower doing their work, and they're not part of the community, whereas we really are very much part of the community. And I think that is an element that has changed. And I would like to see it come back, so we had more interaction on a personal level, and we interested the members of Congress in the process of science. Now, I have a feeling people really don't have a feeling for what is a scientist. Is it somebody in an ivory tower doing things not related to ordinary people's life? And that's not true, because we are very much part of the community. And I think the reason why, for example, life expectancy has nearly doubled during my 100 years of life, and that is in part due to the progress in science in terms of both the lifestyle people have nowadays, and we can now cure many diseases that we had no understanding of at all some 100 years ago. And this is a progress that I think we need to continue. I'm very worried about the current sort of sense of what science is something different, but we are part, scientists, we are part of the community and we want to be understood and communicate. And maybe our fault has perhaps been that we don't communicate sufficiently and intimately enough with members of the public to make them understand what it that this is like. I feel science and art belong very much together, and the creativity that the human mind has can express itself in different way in a sculpture, in a poem, or in a writing, but also in science, because science, the scientific discovery is entering into a forest as if and trying to find your way and discover things, discover new paths to insights and knowledge. Because nature is filled of secrets, and we want to try to understand and learn more about nature. For example, the recent publications about trees in the forest, the trees talk to each other through their roots and communicate. There is a whole world of communication there where I didn't know about. And now it's clear that that is also very important. So we, in science, need to spread our roots into the community at large to make we all understand and talk to each other. That's my hope for the future.
Thank you so much. You made excellent points, and these two major points that you touch on, the communication of the lawmakers and also with the public in general, because we are very bad at communicating to the public in general what you're doing in the lab, and your message is very well taken. Right now, we are in a situation that there's a decrease in budget, and it's probably going to affect science immediately, but also in the long term, I think that's going to be a tremendous effect, because then we are not going to be able to generate this knowledge, curiosity driven, like you said, go in the forest and find out what is in nature. And then later on, this may be applicable to the benefit of society. So what do you see is going to be the next few years in our scientific endeavor?
You know, I am an optimist by nature, and I believe that nothing can prevent human creativity to come forward and express itself. And so it may be a pause, it could be some setbacks, but we are coming, science and art will always be strong driving forces to our existence on this world. So as long as we are alive, we are going to fight for what is our ability to discover new secrets in the world and help our colleagues and friends and the public in general to good health and long life.
Thank you very much. Thank you very much for your participation. I think you are speaking from your office at the Rockefeller University. Is that right?
Correct. That's correct.
I hope you are not work at 101 years old. You are not work today, are you?
Yeah, I try to keep my mind, my balance is not good, but otherwise I'm not demented yet. I can still think, and I think what I said was actually had come to me at night when I think about what would be of interest to say, and not repeat what other people say. So I think I'm fortunate of living not too far from the university. And I love to get to the university to learn to know the young faculty and the older faculty and keep contact with them. And I like to attend lectures and discussions. So the only way of as you get older, to keep your mind going is to be active. I read a lot, and I love. I have, since I was a student, I loved poetry. So I was born and raised in Sweden, so I have a good collection of Swedish poetry, but I also read Russian and other poetry. So life in all areas of science and literature and art is so rich, and I'm so ignorant about everything. So I feel still at 100 years of age, I still feel I have a long way to go before I can comprehend and understand all the things I would like to know about.
If you say that, what else can we say? Thank you, thank you so much for making the time to talk to us.
Oh, it was my pleasure, and I thank you for asking me. And all the best. Yeah, one other thing I like to say before we end our conversation is the importance, as you're an artist or a scientist, is to have, you have to have certain insight, but you also have to have luck in your endeavors. And I think that some of the main discoveries that David Jewell and I did that we received Nobel Prize for was purely accidental. We were just lucky having to do something we thought was not important, but then looking carefully at it, we realized that this was a breakthrough. And I think this, to approach a problem with humility and listen to what nature and what you can learn is the secret to progress. Thank you.
Excellent. Have a good day. Thank you so much.
Thank you.
By the way, Dr. Weisen was always watching live, but we thought that would be better to record, given his age and so on, and the time also. So I want to correct a fact in here before I move on. When I mentioned David Julius, I forgot to mention that he was actually PhD students under Jeremy Turner, and I wanted to have the fact straight, since we are talking about being accurate here. Let's do that. So before we take questions, we continue this discussion, especially address what the Dr. Wiles told us. Let me introduce the next speaker. And we know, as Randy already mentioned, the escalating challenge for the universities, federal investigations, fake investigation, whatever you want to call, or accusations, and they're doing investigating the universities. It's one of the distractions that we are facing. Another one is the proposed reduction in the budget for funding for the various funding agents such as NIH, NSF, DOD, USDA, and so on. So this is a very serious, this is Congress that's going to decide, and fiscal year 26, what's the next situation for the science in this country. And also the draconic reduction facilities and administration fee that used to be 60%, now is about 15%. And another angle of attack is cancellation of grants and contracts. We are very glad that in that issue, we have with us today in the panel one of the lead lawyers that succeed against the administration, Claudia Polskis, a clinical professor of law at UC Berkeley. Claudia, the floor is yours.
Thank you so much. It's an honor and a rare pleasure to be here with this distinguished panel of scientists. This is a very strange moment when litigators are welcome everywhere. So I teach at UC Berkeley School of Law. Being a clinical professor of law means that in addition to classroom teaching, I represent clients in the courtroom and teach students to do the same. And I was invited here today to talk briefly about a lawsuit that I conceptualized in about February, March, when the axe first began to fall on already granted awards to UC researchers, terminated contracts essentially midstream without explanation en masse. And I was waiting for the administration to run to court because these actions were so patently unconstitutional and otherwise unlawful. And as I waited and waited, I kept seeing nothing happening. And as more and more terminations occurred, I thought, I think there might be some collective strategy possible here. And I had sort of intended to write a book on my sabbatical, but maybe there was a greater need in the world than another book. And so fast forward to early June, I filed a legal action in the Northern District of California, federal court in San Francisco, working with my law school dean, Erwin Chemerinsky, and with about 8 other pro bono lawyers that I rounded up from 2 firms, one a class action firm and one typically a defense firm, but neither of them liked fascism and they were willing to collaborate on this suit. And just to put this suit into context, UC system relies currently on about $4 billion with a B in federal grants annually, and thus far more than $324 million of already promised funding has been terminated without cause and without explanation. And so I have been following the chat actively. There are many good questions raised. One is, why are we focusing so much on terminated grants rather than on these vast threats to the federal research enterprise going forward? I think there are a couple reasons. I mean, the news certainly tends to focus on things that have already happened. Everything else is speculative. But the other thing is, from a moral point of view, it's extraordinary to induce all of this reliance on promised money and then, on a variety of bogus grounds to pull that money away. That just violates a very basic sense of justice. And there are really extreme and varied personal consequences. There are people who've set up labs. There are people who've hired postdocs and taken on PhD students. There are people who've committed to conferences that they can't attend and they can't write the papers that were promised. And there's, of course, the vast public good foregone when these very, very exciting research projects get terminated. And so there's a real sort of moral outrage associated with these terminations. And there is something that we can do about it in court. And so in this time of sort of administrative inaction, certainly, faculty have First Amendment right to seek redress of their grievances in court, and the university doesn't dispute that. And it seemed that organizing faculty who had lost federal research grants into a class action on behalf of all researchers who had lost federal grants across the entire 10-campus system might be a novel and potentially effective way to go. And so in the past few months, I've done a really interesting tour of duty interviewing all of these, what I'm calling grant terminees. And the great pleasure in it has just been hearing people talk with such incredible passion about their research, the way people have today. It's really been, a time to see the very best of the UC system, which is not faculty meetings. It's definitely talking to people about their research projects. And so we obtained sworn statements from a number of these people with all of their grant termination correspondence. And these declarations talked about the incredible harm to individual researchers and their students, as well as the public good from terminating these grants. And about a week and a half ago, we got a favorable ruling from Judge Rita Lynn in federal court. The name of the lawsuit is Thakur versus Trump. And the judge said that these grant cancellations were indeed unconstitutional. Many of them violated the First Amendment because grants were terminated for using words like diversity or equity or climate or race. And that was an unconstitutional restriction on speech. And then she said across the board, the grants were terminated in violation of due process and the Federal Administrative Procedure Act, which governs regularity of agency processes, because they were terminated by form letter. There was no individualized analysis of why the grants didn't comport with agencies' missions and so forth. And so this is success in the first pitch of what will be a very long climb, because it's, of course, subject to appeal. But as I speak to you today, I have just an avalanche of really exciting emails in my inbox with lots of exclamation points saying, I just got a notice from NSF that my grant was reinstated. I'm crying. I just got a notice from the National Endowment for the Humanities, to a point in the chat. Let's not forget about the social value of fields other than the hard sciences. And, we never thought this could happen. This is the first ray of sun in a very dark winter. And so I'm not naive about the difficulty of maintaining this victory all the way through. On the other hand, the Supreme Court only has room for 80 cases. We are also litigating as hard as we can and have been litigating this case as conservatively as we can in the event that it does go all the way up. And by conservatively, what I mean is we've focused very much on pecuniary harms to researchers, because those are the ones that federal courts of all political persuasions are most likely to recognize as real harms that should be redressed. They don't care too much about constraint on your individual expression in the classroom and so forth. But if you can say I'm out money, that tends to help the case considerably. So just a couple of things about why we made this a class action. One is, with a class action lawsuit, you don't have to pay lawyers upfront an hourly fee. Everything is done on contingency, although in this case, it's essentially being treated as pro bono work. But there was no way, as just an aggregation of researchers without the university's backing, that we could retain lawyers to put in thousands of hours on this suit, at several $100s, if not $1,000 per hour. The other thing is that a class action enabled us to take a handful of researchers, the so-called named plaintiffs, and tell their stories as exemplars for the whole university without having to bring every single researcher into the suit to get relief for all those researchers. And that was important because the other scenario is not possible. Finally, and this really goes to the storytelling point that's been emphasized by everybody so far, I thought a class action in which you had individual researchers putting their names on a lawsuit and telling their stories in multi-page declarations was a very powerful way to talk to the public about why university research actually matters. And in that way, our lawsuit is quite different from most of the lawsuits that have been filed about grant terminations, such as lawsuits filed by the American Association of University Professors or American Association of Universities or state attorneys general, where you have essentially institutional actors speaking. And that can feel a bit distant and disembodied. And having the individual researchers, I think, really shows both the individual human investment in the research enterprise and also the human toll of terminating these grants. And so I'm hopeful that this suit, if we succeed, can be a model. I've certainly gotten a lot of inquiries from elsewhere in the country about how can we replicate this. We thought our administration would rush into court to try to reinstate these grants, and it hasn't happened. This seems like a way for faculty to self-organize and so forth. So if nothing else, I hope maybe this is one piece of provisional good news and a very dark forecast. And I also think, to bring the themes of current funding and future funding together, that there are some lessons here for how we should organize ourselves going forward. One thing that's very clear is that our structures and also just our institutional culture in the university are ill-suited to protecting our collective interests in ongoing research funding. A colleague once helpfully explained to me, when I was very new to the academy, that a lot of the odd disconnects I was experiencing were a function of us being a community that is united by our shared commitment to autonomy. And I think that's very apt, and it's the source of some of our predicament. When I was interviewing different researchers who would be potential plaintiffs in this lawsuit, I just heard time and again how distressed they were that they were struggling with these terminations and all of the decisions they had to make in their wake absolutely alone, that there were no practical support structures, there were no emotional support structures. Everyone was just staying up till 1 a.m. by themselves, thinking, who should I fire first? Should I order these supplies and hope I can bill them in my closeout paperwork or not? And we had absolutely no mechanism for bringing all these people together and saying, how do we help you through this crisis? And also, what are the solutions going forward? And that brings me to the issue of sort of what's the role of faculty and what's the role of administration. One of the things that's been interesting to me in listening to people today is that many people have said, yes, we need to do a better job of selling the value proposition of scientific research to the public, and we need our leaders to do that. You're actually all leaders. That's why you're on the call. I haven't heard that many I statements. I really think that in addition to publishing in science and so forth, I should think about where I can write an op-ed in a swing state with a farmer to explain my research to a very red district. All of you have a lot of agency. And I'm really struck by how many conversations I've had with people who have more agency than almost anyone in the world, saying that they're really kind of powerless to change this conversation. I don't think any one person can change it, but I do think we actually all have a pretty privileged platform. We have a lot of media access, and we should use it. And then I think this leads me to, ways that I think our incentive system probably has to change for people to spend more time engaging with the public so that ultimately the public supports us in times of political need. So, I mean, I know talking to colleagues that until very recently, it was actively sort of disfavored to write something like an op-ed. My experience, as a reader, is that it's really fantastic when somebody can actually concisely and persuasively explain to you what they do in 650 words. That's a lot harder than, banging on for 80 pages with 500 footnotes. I mean, I've done both, and I think, a tiny op-ed is one of the most persuasive vehicles we have. And so I think we need to incentivize people to do more engagement with those beyond university walls. And, if you publish an op-ed, if you publish it in the New York Times, that's better on your CV. But as people have said about the echo chamber, that really guarantees that it will not reach the people whom it needs to reach. So we have to do a lot more thinking about how we can, operate in these two registers, right? We can still do our academic thing, but we can also be much more strategic about where we do our popularizing so that it can have political effect. So I'm happy to continue any of these conversations offline. I'm, full of admiration for all that you do. And I, in conclusion, I'm thinking about this saying that I read at a national park in Ecuador, which in translation read, people protect what they love what they understand. And I feel like we really do have to go back to figuring out how to get the public to understand what you do so they can love it and they can rally and support. Thank you.
I think that was Maya Angelou who said that.
Okay, thank you very much, Claudia. So Claudia almost became an entomologist. And if there is anything that the great Tom Eisner failed, was to convince Claudia to join his lab. John, can you hold for a second there? I want to read this question here from Ting that says, how about forming a coalition of scientists and journalists exploring a way of communicating research funding in plain English, so that the general public get a better understanding of how scientific research can benefit in their daily lives. Here's one example that was submitted by Steve Palumbi.
I'm Steve Palumbi at Stanford University, and a lot of the work that has been supported in our lab by NSF has been on the mechanisms by which reef-growing corals are affected by heat waves. They bleach, they die, they wreck reefs because of their sensitivity to heat. And so our research is on the mechanisms and the genomics and the intricacies of that. But along the way, we've realized that we actually know enough already to start using that information to help. And a lot of the work that's going on now is taking that basic science and turning it into a way to help people help their own reefs. We've designed very inexpensive, rigorous equipment that will allow people to test corals for heat resistance. We train them to use that in places all over the world. And then they can find heat-resistant corals to put into restoration settings or to put in marine protected areas. And that takes the basic science, which is still ongoing and is fascinating, but turns that basic science into something that helps people right now. That helps in places like Hawaii. It helps in places like the Caribbean, in Florida. It helps in U.S. military bases around the world. It helps in countries that are great allies in the Pacific and all around the tropical world. So putting that tool into people's hands, training people to do that, training our grad students and postdocs to help people in the rest of the world has been a huge bonus to this basic research.
All right, thank you very much, Steve. There are three very important questions here for Claudia, but John Hildebrand has his hand. John.
Yeah, I just wanted to follow up on a nice prompt from Claudia. We all have agency. And just as an example, and I don't think anybody has said anything along these lines yet, for the last 30 years or so, I've been taking every opportunity to talk to kids in elementary schools about science and how science works. Kids in this country don't benefit from any kind of national standards. It's all up to the local school board what they do, and most school boards don't have anybody knowing much about science. So science is taught as a bunch of facts that kids have to memorize, and they hate it. They find it dry and uninteresting. That's the antithesis of what we all know science to be. So when I talk to second graders and fourth graders, which is the most enlightening and exciting thing I do in my career, I'm having the pleasure of seeing kids understand that science is a wonderful process. It's not a bunch of facts that you memorize. We all have agency to do that. We all have agency to talk to people in our school board, to help them understand science and what's needed, and even to get into the classrooms ourselves and talk to the kids and show them what an experiment is and how we can correct a misunderstanding. Kids don't learn that in the way we teach science in this country. So just channeling my dear friend Bruce Alberts, who would be talking about education if he were here, we all have agency to do something about it right in our own communities. And I hope we'll all take advantage of that possibility.
Thank you very much, John. The National Academy of Engineers has a new president that starts today, July 1st, and we are very pleased to have her here. Sujai Leal is the next the president of the National Academy of Engineers. This is the first day on the job, and she made the time to talk to us because we spoke about this natural science and the this and that, but we didn't mention anything about engineer. So you have the floor now, Sujai.
Thank you so much. Hello, everyone. With regard to engineering, well, engineering, I consider it the engine of innovation, but we take knowledge that is discovered by scientists to turn them into useful technologies that will benefit people in society. So one prominent example that I'm familiar with personally is the proliferation of information technology that we are all dependent on today, including to hold this webinar. Our cell phones, our computers, cloud computing, that would not have been possible without federal funding of research that showed the industry, the semiconductor industry, how to miniaturize, how to shrink transistors so that more of them can fit on a chip. And so these chips are the electronic brains of all the devices that we use today. And so that, you might know a brain has roughly 100 million neurons. Today's semiconductor chips do have over 100 billion components, transistors. And the only way that was possible is to make them very small, to make them miniature. And so back more than 25 years ago, we were looking for a way to show that transistors could be shrunk to be so small. And we relied on semiconductor solid state physics. We relied on quantum mechanics and also chemistry and material science to find a way to make these transistors smaller. And that has enabled computing technology to improve at an exponential pace, leading to the age of artificial intelligence today. And you can see the tremendous impact in all sectors of the economy. And that would not have been possible without fundamental research funded in engineering funded by the federal government in the late 1990s.
Very much, and the Marcia McNatt was applauding there. No one saw that, but she was behind the scenes. They applaud that he have a new president. And advice to her, President McNatt. No.
So sorry, yes, I had to get myself off mute button. Well, first of all, we're thrilled that Sujai has joined the Academy. She has an incredible reputation for what she's done with engineering, and she is also an effective communicator. So that's what I love about Sujai. The other thing about Sujai is that she is eager for change. And I think that's something we maybe haven't talked enough about today, is the fact that with all of these challenges to science, we have to look carefully at ourselves and make some good decisions about how we are going to increase the efficiency and effectiveness of our scientific organization. Even before this administration, we were seeing other nations catch up to us. Randy talked about how China's investing greatly and has already surpassed us in terms of investment in science. So they took our model, and they're a bigger country. They're using our model very well. But what we do in America best is innovate. We have to innovate in how we're doing our research so that we can not be competing against China playing the old game, but come up with a new game. And I think, honestly, I think AI is going to be a game changer here, both in education and in research.
Very good. So let me show another example here of a powerful message to the
Hello,
public.
my name is Susan Strom. I'm a professor emerita at UC Santa Cruz. I want to tell you the story of my grandnephew as it highlights the huge benefits of research-driven medical advances, in this case, medical advances in the area of cancer. My grandnephew James was diagnosed with glioblastoma at age 7. Glioblastoma is an aggressive brain cancer that's usually fatal, as in the average survival time after diagnosis is about 1 year. James immediately underwent surgery to remove as much of the tumor as possible. Then 6 weeks, 33 sessions of radiation of the brain tissue around the tumor, then another brain surgery, and then chemotherapy with the drug Temodar. He was a real trooper through feeling lousy due to the treatments. He knew his brain tumor was life-threatening. He wanted to beat it and be a hero, be a beacon of hope for others diagnosed with glioblastoma. And he did it. He beat it. He was diagnosed at age 7. He's now 17. He's an outgoing teenager. He loves camping and fishing. He's a passionate and accomplished woodworker. Here's my pen. And he just got his driver's license, a big accomplishment. Cancer research is an area where the discoveries and advances are coming fast and furious, including sequencing the DNA of cancer cells to identify genetic changes that contribute to that cancer and to enable personalized treatment for that cancer. Critical cancer research is in the crosshairs of cuts to NIH and NSF. We all need to speak out opposing those cuts in order to save future victims of cancer like James. Thanks for listening.
Very powerful message. I'm glad that I was able to get Susan before she left for Mexico. So we're going to open for questions, but I wanted to start with this question here from Danielle Cox. In the lawsuit from Columbia faculty, the judge decided they lacked the study because presumably the grants went to the institution and not to the faculty, and Columbia did not join. Is this a problem going forward? And maybe Claudia could combine with this question here from Claudio Fogo that says, in view of initial surprise, your initial surprise at the fact that UC Regent administrators did not even think about initiate a lawsuit, and the efficacy of a class suit, isn't it about time to discuss changing in the autocracy structure of university governance? So that two things that Claudia may be able to answer, at least one of them.
Sure, I'll try to be brief. Big topics. The first question, which is really a legal question, is it a problem for us going forward that the university is not a party to the suit? Because, as was rightly noted, in a somewhat similarly structured suit, it was a problem for researcher litigants that Columbia University, which technically has the contract with the federal government, was not a party to the litigation. And as I think I just wrote in the chat, in our case, we were able to distinguish it on a couple of grounds. One is in the Columbia case, the university was actually very hostile to researchers bringing this suit. Columbia was in the process of trying to cut a deal with the Trump administration. And so you had this non-alignment of interests that made it very awkward for the court. But in our case, we were really able to convince the judge that just because the university is injured by these grant terminations, and surely it is. It's lost its indirect rate, it's lost, reputation and so forth. It's lost its ability to attract students and faculty in the long term. That doesn't mean nobody else is injured. Standing is not a mutually exclusive concept. Many parties who are injured can have standing to be in court to litigate those injuries. So this wasn't a problem in our case. That we did brief it, the judge analyzed it. The other thing we were able to point out, which I don't think was a point made in the Columbia litigation, is that the government actually had two different arguments for why our researchers would lose. And, in law, they always say, like, if you don't have the law, pound the facts. If you don't have the facts, pound the law. And if you don't have either, pound the table. In this case, the government definitely did not have the facts. I mean, if you read these termination letters, they're just farcical. They could be in a comedy sketch. And so, procedure is always kind of the refuge of the scoundrel in law. And so they had two procedural reasons that researchers couldn't bring suit, even against actions that were obviously illegal. And one of the reasons was what we've just discussed. They said you don't have standing because only the university can sue, because the university signed the grant paperwork with the agencies. But the second was, they said these are essentially lawsuits about terminating contracts. And there's a special court, the U.S. Court of Federal Claims, that's just for bringing contract breach suits against the government. And that's where you should be. Now, that's a huge problem for lots of reasons. The Court of Federal Claims really just deals with individual contract disputes, and you couldn't have a class action in the Court of Federal Claims. Every single researcher would have to be a litigant. It's more for like a Boeing when the government defaults on payment for, 1,000 airplane parts. It's not where we belong. We belong in a federal court. But anyway, we were able to point out that the argument the government was making was actually, inconsistent, because if we were supposed to be in the Federal Court of Claims because these were contracts, then the researchers were parties to a contract, and then we had standing. And if we didn't have standing, then there was no way we could be in the Court of Federal Claims. And so they had to kind of choose an argument. And I think the judge was persuaded that was just completely internally inconsistent. And so that has not posed an impediment. Switching to this second and larger question about, university governance, I was really distressed in many, many meetings that different permutations of university leadership had in this time with affected faculty. I'm just going to be blunt at how patronizing the administration was to the affected faculty at a time when they really should have been collaborating on solutions. I think everyone here who has, cracked the codes of mRNA and everything else you've done is quite capable of thinking intelligently about the problem of funding diminution. And all the administrators seem to say to us is, don't worry about it. We're having lots of meetings. We have very good minds on it. We're taking it very seriously. And we just kept getting these kind of butts in chairs metrics. Now we have 17 people thinking very hard about it in very long meetings, and now we have 27. And there was just never an open invitation to engage as equals in solving this structural problem about how we're going to backfill terminated grants if they don't get restored by courts, and going forward, how we're going to make the best collective case for university research funding. And to me, that's very sad. Obviously on paper, we have shared governance in the UCs, but operationalizing that, particularly in a time of crisis, is something different. And I do think this is a moment to really revisit the structures we have for addressing these very deep problems, which will persist.
Thank you, Claudia. So there are so many questions for Claudia that would warrant one single webinar just for her to speak. But let me ask another question here so that maybe some other colleagues might chime in as well. This is a question from Melinda. This is fundamentally a political problem. I really don't think it boils down to convince the population that science is valuable and good. I am certain that there are academics and scientists who vote for the administration and this agenda, never believing that they themselves would be target. Misinformation about science and universities is being deliberately generated and spread. I have countered unbelievable statements from intelligent people who have been duped by lies and misstatements in the media. How does this group plan to address this current and appalling reality? So anyone from the panel, maybe one of the presidents of the National Academies, Marsha, would you be willing to chime in on that one?
I'm not sure how many of you saw the Washington Post this morning, but they fact-checked Donald Trump using 4 or 5 different AI chat boxes. And they published the results. And basically, anyone could take a statement from Donald Trump, put it into an AI, and get an answer, because I actually felt that the answers from AI were very couched in appropriate terms, but very clear that this president is stating falsehoods regularly. And there even was a sense towards the end of the article that although we are perhaps too complacent with allowing falsehoods from our political leadership, that the current president has reached a new height in terms of falsely claiming things as fact.
Thank you. Looks like Randy wants to chime in on something. No, not this one. All right.
I would just clarify that I would call it a new depth, Marcia, not a new height.
All right, so let's move on here. Let me show another example of how scientists discovered that their curiosity-driven type of research has generated so much resource for this society in general.
Hi, I'm David Patterson. I was a professor of computer science at the University of California for 40 years, and I'm going to quote from this paper that's about to appear about one of the 4 or 5 case studies of successful research projects based on government funding. This one is RAID, for redundant arrays of inexpensive disks. If we go back 40 years, when the Macintosh came out, those early users, when they needed storage, had to repeatedly insert and replace floppy disks, which is a real pain. 3 years later, they brought out a hard drive that didn't rely on the floppy disks, that was a godsend for the computer users. This project got started when my colleague Randy Katz asked the question, what else could we do with these hard drives, these small hard drives? At the time, in mainframe computers, these hard disks were the size of refrigerators, weighing hundreds of pounds and losing lots of power. Well, these small drives were tremendously smaller and lower power. And in fact, this shows the relative size. The question that we asked, well, what happens if we place one of these big mainframe drives with 100 small drives? And that led to this paper, and that we calculated that if we were to use some math and add some redundancy, we could even be more reliable, because you could recover from errors, as well as much lower power, smaller space, and higher performance. This paper had impact around the world, but particularly in Boston. The company EMC, which was founded to make memory boards for mainframe computers, was forced out of the business, so they needed a new product. They read the RAID paper and announced their first RAID product in 1990, Symmetrics. They shipped $25 billion in just 7 years, and many other companies also ship products. So surely there's $100 billion in sales. To put that in relationship to the NSF funding investment, that was about $1 million in today's. So that means it was 100,000 to 1 of the return on the government investment. Since at least 10% of sales goes back to the federal government in taxes, the return to the government was 10,000 to 1. Now, not all researchers are home run. About 5 of my 10 projects, I think, were home runs, but 5 weren't. So overall, it might be 1,001 government taxes. And I encourage you to read the paper when it comes out. Thank you.
Thank you, Dave. Very nice statement there. May Berenbaum. Glad to have May Berenbaum in the panel of guys. She's a world-renowned entomologist and the editor-in-chief of PNAS and so on. The list will go on, and the National Medal of Science recipient and so forth. May?
Oh, well, I know it's late, and the only thing I wanted to add is something that hasn't come up yet, and it's a very powerful tool that we can use as scientists in facilitating information exchange and communicating and allaying concerns, and that's humor. It's not the easiest way of communicating, and it can go horribly wrong if improperly implemented. But it does have an effect of lowering barriers and establishing connections, and I recommend it highly.
Very good point. So someone talk also about the social media. Looks like Marcia has want to chime in on this one. Please go ahead.
I just wanted to underscore what May just said, because the trick is getting your message to people who either have no interest in science, who have no time for science, or no trust in science. And one of the programs we have at the Academy is called Three Comedians and a Scientist, or something like that. And it uses clubs in New York and LA to pair a scientist who's, amusing and pretty good at dealing with the public with a couple comedians. And people come in for comedy night. And yet they end up walking out with new appreciation for science and what science is doing. And so I just wanted to say it's reaching those people who would not even read a science editorial if it were written in Breitbart News, probably.
Thank you. I asked a few people to contribute some short statements via video, and here's an interesting one from Arturo Casadevall from Johns Hopkins.
When I was in medical school, a new disease emerged, something that had not been seen before in medicine. This was AIDS. This was 1981, and I was in New York City at the epicenter of the then developing pandemic. Within 3 years, the cause was identified by researchers at the NIH and in Paris. That is the HIV virus. When I was training at Bellevue in the mid-1980s, all the patients who had AIDS died. We could treat their infections, but we could not treat the underlying illness. 10 years later, the first drugs became available, and it was an amazing result. These individuals were able to resume normal lives, and the immune system came back. Today, 40 years later, we have tremendous drugs that essentially allow these patients to have normal lives, prevent others from getting infected. This all came from NIH research.
Thank you very much, Arturo. Very important statement right there. We didn't talk much about the training of graduate students and so on, training grants and the importance of that. I have a statement here from Greg Pask from Middlebury University.
I'm an associate professor of biology at Middlebury College up here in the Green Mountains. And federal funding has had such a major impact in my training and the training of others. So back when I was doing my graduate school work, I got an NIH pre-doctoral fellowship that enabled me to get the training and the financial support to do research on the olfactory system, or the sense of smell of mosquitoes, figure out how they're able to find us and bite us, transmit some potentially dangerous diseases, and kind of understanding the chemicals that we might be able to use to push them one place or attract them to another. So really, really powerful stuff that enabled me to kind of launch my career as an insect chemical ecologist and neurobiologist. Flash forward to today, now we have National Science Foundation funding to study the olfactory systems and figure out how these little fireflies are communicating, whether it's by flash patterns or by these that don't produce any light as an adult, using a chemical system. And with this, I'm training several more students for getting real life experience and hands-on experience in science. And then they're going on to several different careers. Some are going to medical school, other medical professions. Some are going to graduate school to look at biomedical research or other things in conservation biology and climate change research. So the wide-ranging effects of what federal funding can do for science and the training of scientists is immeasurable. And we hope that kind of there's continued support of federally funded research because of these manifold outcomes. So thank you.
Thank you very much, Greg. Very good statement there. Before we go to another set of questions, let me move here to another statement from UCLA. Karen McKinnon from UCLA speaking to us.
Hi there. My name is Karen McKinnon. I'm a professor at UCLA in atmospheric science, statistics, and the Institute of the Environment. Today, I want to talk to you about the work that's been done in my group on understanding heat extremes. Heat extremes, although they're less visible than other weather hazards such as a tornado or a major thunderstorm, are actually the most deadly weather hazard in the United States and in the developed world more generally. And we know that they're going to increase in severity and intensity and in length as we go into a warmer future. The work that we do tries to improve our understanding of heat in a way that we can produce information that is usable for people who want to try to adapt or plan for a future warmer world. That's played out in a few different ways, funded by a range of federal agencies, mostly the National Science Foundation, but also the National Oceanic and Atmospheric Administration, or NOAA, as well as NASA. One major question that we've had in the group that we've recently been able to answer is exactly how heat extremes are changing and if they're so-called, amplified compared to changes in other temperatures during the summer. So we wanted to understand, are heat extremes actually warming faster than typical summertime temperatures? In recent work, we were able to demonstrate that that is not the case, and this important result allows us to get a better and more accurate estimate of how we might expect heat to change in the future. We also have identified different mechanisms that can cause or amplify heat extremes, including the role of the land surface, such as how much moisture there is in the lands, how many plants there are on the surface, amplifying or damping heat. And this has similarly allowed us to make another important finding, which is to identify potential precursors of heat that allow us to predict heat waves on the order of 5 to 7 weeks in advance of the heat wave in the central and the eastern US. We are currently working on expanding that type of research to identify other cases where we might have long lead predictability of heat in order to better prepare for these types of impactful events.
Thank you very much, Karen. Any other comments from the floor, from the panel? To Jay was look at that and with much appreciation for the work that she's doing at UCLA. Any comments? If not, I'm going to play another one very quickly, and then we open the floor again. So that would be Sunny Ramaswamy, former director of NINFA.
My name is Sunny Ramaswamy. I was appointed by President Barack Obama to serve as the director of the National Institute of Food and Agriculture, NIFA, as we call it, the extramural science agency of the United States Department of Agriculture. I finished my 6-year term in the first Trump administration. For those of you that don't know, NIFA catalyzes transformative discoveries, education, and engagement to solve societal challenges by supporting basic and applied research undertaken by universities and others that result in innovations to secure our nation's preeminence in the food and agriculture enterprise. Agriculture and food are essential for American health and prosperity, and they represent a $1.55 trillion enterprise in this country. Agriculture faces complex challenges, including economic pressures of rising input costs, labor shortages, and a widening trade deficit requiring solutions. In addition, there is need for ensuring resilient and sustainable farming practices in the context of the environmental challenges, such as diminishing land and water resources, climate change, and the emerging biological threats. NIFA's investments have generated innovations that are an engine of economic growth and development, critical for America's continued global competitiveness. Additionally, NIFA supports workforce development, including training of future scientists and training and development of farmers and the workforce in general. NIFA also supports positive youth development through programs such as 4-H and FFA, focused on hands-on learning, leadership, experiential skills development, and community engagement. The programs supported by NIFA ensure our nation's food security, agriculture and biosecurity, economic security, and ultimately, national security. The administration's 2026 budget request is proposing a $600 million reduction to NIFA's budget. If enacted, it would be devastating to the food and agricultural innovation engine and have long-term implications to our nation's global competitiveness. Thank you very much for allowing me to share a few thoughts about NIFA.
Thank you, Sonny, for participating. I'll ask Steve Palumbi is also in the panel. He provided that very nice short video. Steve, any comments?
Yeah, thank you, Walter, very much, and I really appreciate this incredible panel. I totally agree that reaching people with messages is incredibly important, and these examples of how research that was really started as discovery, finding basic research have led in pathways to helping people. Those are critical messages to come through, and showing how that happens, not just from the academy on down, but actually to individual people's lives is amazingly important. Keeping on doing that, and if all of us think like, well, how have these things moved into society is a really important part of our job, and then communicating them, whether they're to elementary school students or to comedians in improv settings, or to op-eds or to just your neighbors is a really crucial part of what we're facing now. So, thumbs up for all of that.
Thank you very much. Here's another statement from another junior faculty.
Hello, everyone. My name is Jason Pitts. I'm a biologist at Baylor University. Research in my lab has been supported by the National Institutes of Health, and our projects have focused on sensory systems in insects, especially mosquitoes and flies that transmit pathogens that cause diseases in people. Although most of our work is basic science that revolves around chemical ecology, that's how chemicals in the environment that are emitted by one organism influence the behavior of another. There are very practical applications to our work. So, for example, we could see improvements in surveillance and trapping of mosquitoes and other biting flies, and also the development of novel repellents that can protect public health. We think that the principles that we learn can be used by other scientists in our field to inform their studies of, for example, insects that cause devastation to crops and to stored food products, and vice versa. We're informed by the studies of other scientists, and we share information through science conferences that we attend and through our publications. But in addition to the basic science and translational science, federally funded research supports training of students. Training of students in my lab covers all levels, from the least experienced undergraduate who's getting their first experience in a laboratory, to doctoral students who are looking to academic careers, to postdoctoral fellows who are ready to lead their own research labs. So all these are important. It's also important to note that many of our students will go on to professional careers, and say in medicine, where they're using evidence-based decision-making models for the benefit of their patients. So in summary, I and we support federally funded science. It has had a demonstrable, positive, and irreplaceable, arguably, impact on human history, and we think is important for the future of humankind. So thank you for your time. I appreciate the opportunity to comment. And thank you to Walter for putting together this workshop.
Thank you very much, Jason. Randy?
Yes, thank you, Walter. I realize our time is past, and I probably should have raised this point before, but I like to emphasize that the current situation is rather unique. During Trump's first administration, he every year proposed a significant cut in federal funding of science, and every year that was overturned by Congress. In fact, over decades now, the Republican Party has been very warmly supportive of basic science, in some cases more so than the Democrats. So we face a unique situation, which I think is attributable to the tremendous political polarization in this country. To sustain the efforts of the Congress in supporting science, at least among biomedical research societies, there was, and I think still is, a Congressional Biomedical Caucus, which appeals to congressional staff and to Congress people who would come once a month to hear a lecture from some scientist who's very skilled in sharing his or her information with the legislature. And whatever efforts of that sort have continued have now fallen on deaf ears, I fear, because of this tremendous political polarization. So this is not, this is not a long-term decline. This is a sudden, precipitous drop that we face.
That's a very important point and very timely. Anyone else would like to add on this particular topic? John Hildebrand, Marcia McNatt, Jay. No comments on that. That's a very timely point. And let me share another statement, video statement here very briefly. This one coming from Arturo Casadeval.
In 1988, I went to Jacobi Hospital, part of the Einstein Montefiore Medical System, to do my infectious disease fellowship. At that time, we also covered pediatrics, for the pediatrics patients. In those days, roughly once a week, a baby or toddler would come in with Haemophilus influenza meningitis. This is a very serious disease. 1/3 of the kids would die. 1/3 of the kids would have left with neurological defects, learning disabilities, and the others recovered, although we don't really know what the long-term consequences were. Then in the early 90s, a new vaccine was introduced, a conjugate vaccine that had been developed by the NIH. Within a few years, the number of cases dropped such that by the mid-1990s, the disease had gone away. Think about what that meant. All those parents did not lose children. All those parents did not have impaired children. All those children who went on to live lives. And this was the result of the Haemophilus influenza type B vaccine developed by the NIH, which is a remarkable public health advance.
How can society live without vaccine, without science? That's a big question now for everyone. So I'm going to ask all members of the panel to make the final statements, and then I'll continue and I'll play a couple of videos that are still left. And because it's already past time, and I appreciate you always stay long. And I'll start with Claudia. Claudia, any other closing statement? We don't have time to answer all the questions. Hopefully, we are going to do that offline.
Well, I guess all I want to say is that victory is obviously not guaranteed, even if we fight, but if we don't, defeat is certain. So I really hope everyone, despite the overwhelmingly negative news coming in, will use whatever agency and energy and creativity they have to push back against this. It's not over till it's over.
Thank you very much. What about John Hildebrand next?
Yeah, I'll just echo what I said before and what I think Claudia said. We all have agency. We shouldn't be sitting on our thumbs. There are things we can do right in our own communities, and we should be doing them and not just talking.
Marcia McNatt.
Yeah, I guess my only final statement is that I've been up on Capitol Hill, and I've talked to a lot of the Republican leadership, particularly in science and commerce and other areas like that. There is still really strong support for science on Capitol Hill. The problem is they're frightened to death of bucking the president. And I think we need to figure out some way that they don't view it as political hara-kiri to go against anything the president says.
Thank you very much. Jay.
Yeah, I fully agree with John and Marcia. We need to find a way to depoliticize science and tell the story. So thank you, Walter, for gathering all these stories. I think all of us can learn to share these stories, not only our own stories, but these stories that we learn about. Let's just share them and have them touch the heart of people in leadership as well as the general public. I think we need to all contribute to increasing public understanding and appreciation for science and somehow depoliticize this.
Thank you. Brandy?
Well, my view is that science, and the two examples that I gave, are not political at all. They're basic curiosity-driven exploration of the natural world that are the subjects are neither Democrat or Republican.
That's right.
So
yeah, I think, Randy, what's different right now is that while the administration is pretending that science will be fine even with the cuts, the reason they're doing the cuts is because they have to come up with some offsets for their taxes. They want to keep taxes low. And so that's why everything else, Medicaid, science, weather forecast, everything is FEMA, everything's being cut. And it's all for these tax advantages, which are a short-term win for the Republican Party and a long-term loss for the American public.
Well, we need to counter that. I mean, it's in fact, the cuts are not uniform. As I pointed out, the aerospace and defense industries are not being forced to conform to a 15% overhead. SpaceX has 100% overhead or more. So it's clearly those decisions are political. I think the administration properly views the academy writ large as a bunch of liberals who never vote for Republicans anyway, and so we're easily dismissed, and that puts us in great peril.
Thank you very much. Thank you all so much for being here in the panel. I'm going to continue with a couple of videos that I still have. You don't have to stay if you don't want. You are welcome to stay, but I'm going to continue with these videos and finish. And before I do that, I want to say that I wanted to dedicate this presentation today, if I can find the proper place here. Looks like I cannot. Yes, I found it. I want to dedicate this event to our friend Jeff Aldrich, who just passed away. This is the first entomologist that I met in a meeting. I was in Japan, and we both came to a meeting in Brazil, and he used to work with an insect, Hemiptera, that's called true bags. And his words, he always says, I work with true bags, the other insects are cheap imitation. So we miss Jeff very much, and we're sad for his passing at this time that I was, as people know in chemical ecology, when some big figure in entomology, in chemical ecology passes, I create videos and tribute video, but I was so busy with the preparation for this event that I didn't have time to make one for Jeff. So let me play a video here, a very short one from Peterburg about the importance of science in his view.
Have you ever sent an email, surfed the internet, made a cell phone call? Well, you've used quantum mechanics in basic research results, because without quantum mechanics we wouldn't have semiconductors, and without semiconductors we wouldn't have cell phones and the internet. Basic research is very important for all these topics, and if we stop doing basic research, mankind will stop to have new technologies like the internet and cell phones.
We have many contributions, the outstanding scholars from all parts of the country, and some of them could not even send a video itself, but send some statement, and I was able to use these statements and to create a video for them. Here's one example. William A. Gardner, a professor emeritus of the Department of Electrical and Computer Engineering at the University of California, contributed with a reflection which I summarize for you here. In his reflection, Bill accounts his academic career and its significance, as well as its impact on national security and communications technology. Beginning at the Bell Labs in 1967 and joined UC Davis in 1972, Bill pursued high-risk, theory-driven research that was initially viewed as impractical. His work led to a paradigm shift in statistical time series analysis, centered on a property called almost cyclostationarity, which transformed how signal interference is addressed in multi-user communication system. This new theory laid the ground for major advancements in both commercial and classified communication technologies. It influenced the cellular telephone industry with outcomes like patent sales to Apple and intellectual property sales to Lockheed Martin. It had a profound but classified impact on U.S. communication intelligence and national security through work funded over 25 years. Bill emphasized that such groundbreaking innovation was only possible due to the academic freedom and long horizon risk tolerance uniquely found in well-funded academic environments, not in profit-driven industry setting. He warns that reduced federal funding for academic research threatens this environment and the risks further diminish fundamental scientific breakthrough, which are necessary to sustain the long-term technological progress. Thank you, Bill. A question that the people ask very often is that we pass through this university campus and they are making new buildings all the time. And the question is that why they don't use this money for research. I asked this question to President Mike Crow from Arizona State University.
Let's take a look at this question. So buildings are a function of, office space for staff and dedicated specialized space for research. And those are usually projects that have a 100-year lifespan. They're financed over a 30-year time frame. They're usually debt financed over these time frames at low interest rates because of the public purposes of the universities. And so they are small expenditures on an annualized basis over 30 years with annualized operating costs compared to research. So we might spend $20 million to set up an engineering professor working in some advanced area of material sciences, and then they would then move into a building that's already built that then might have a several million dollar renovation for them to move into that space to do their particular experiments. And so there's a huge difference between the capital costs of experiments and the actual conduct of the research itself. In fact, the complexity that comes along with what's called direct costs for research or indirect costs for research. This is an 80-year-old model that was assigned to the universities 80 years ago as a way of keeping the faculty member and the cost for the faculty member, the thing that the government would spend directly for, and then the university would be reimbursed for all of its other costs, the cost of electricity, the cost of animal care, the cost of buildings, and so forth and so on. So the question says, well, why is there always money for buildings but not for research? It's not really true. The buildings are small by comparison in terms of their actual cost to the research itself. In our case, maybe we're spending tens of millions of dollars a year on debt financing for buildings over long periods of time. It could even be $100 million a year at peak moments of building over 30-year stretches. And the research that we're doing is in the low billions of dollars, just above $1 billion per year. And so it's just a difference in scale, and the buildings are more like a disposable thing. They're more like a car that you're using to do the research, and they're very much different than the actual conduct of the research, which is principally related to people and equipment, particularly highly specialized research equipment, in many cases, unique devices, systems, and tools.
Last one, this is one truncated a little bit, but the last one is top 10 reasons to fund research in academia that David Patterson wrote.
So the first reason is that universities publish their results, whether it succeeds or fails, so that everybody can learn from that effort. In an associated video about RAID, redundant array of inexpensive disks, EMC Corporation in Boston built products based on those ideas without ever interacting with us, just by reading the paper, and that led to hundreds of billions of dollars of sales. Most companies have no such tradition about publishing. The second reason is successful university research projects can lead to new companies. Over my career, there have been numerous successful startups based on university research that have become major corporations. It can be challenging to spin out a company from a large company when that large company owns the intellectual property rights. The third reason is that university projects are inherently multidisciplinary, and that's one of their strengths. Where else can you get world-class experts in science, engineering, arts, and so on in one location and get them to talk to one another? Research in the intersection of computer science and other fields have led to many innovations. For example, top experts in computer science and top experts in neuroscience collaborate together on my campus to be able to read the minds of people amazingly using MRI data. The fourth reason is that academic freedom enables exploration of unconventional ideas. Academic researchers have intellectual freedom to pursue high-risk, high-reward ideas that may not have immediate commercial applications. For example, the RAID project that I just mentioned was a byproduct of curiosity-driven research. A faculty member wondered what we could do with a new technology. Industry, in contrast, is typically more risk-averse and more goal-oriented, understandably more focused on deliverables with short to medium-term payoffs. The fifth reason is that it can be awkward for companies to develop technologies that disrupt the current product lines. An academic's only concern is to advance the state of the art. For many of the home run labs that in this paper, that we had 5 of them, one of the last companies to embrace those ideas was the leading company in that field. They were pretty happy with the current marketplace and very profitable and had little desire to change. Christensen refers to this as the innovator's dilemma in his book. The sixth reason is that industry has reduced the amount of research funds over my career, especially for this high-risk research, is what we're talking about for these university research labs. The computer science labs that played these huge roles in the 20th centuries are shadows of their former selves today. Most companies focus instead on advanced product development. Our society relies much more on government-funded academic research than it was when I started my career. The seventh reason is that top universities attract top people from around the world. Academia attracts these very bright people who want to get advanced degrees, and some of those who get advanced degrees go on to lead large companies. Examples of the CEOs are of AMD, Google, and Microsoft are people like that. And sometimes they found new companies like Hewlett-Packard, Intel, NVIDIA, and Netflix. Ensuring that universities, US universities, can draw from the brightest of the 8 billion people around the world, which is 25 times larger than the population of the United States, has been and is vital to the US success in science and engineering. The eighth reason is that even projects that aren't home runs train students. After graduation, they can become innovators and make their own contributions. While universities produce novel ideas and transfer technology to existing companies and startups, their most important product is people. The silver lining of research projects in industry that do not pan out is less clear. The ninth reason is that computer science is a young person's field. Our technology changes so rapidly that the state of the art 20 years ago or even 10 years ago can be nearly irrelevant today. A student may have better knowledge of the most critical material than someone with decades of experience. Having a research staff by brilliant, hardworking, up-to-date young people with less experience is not necessarily a huge disadvantage for research in computer science. The last reason, my 10th reason, is that funds go much farther at universities than in industry. Faculty salaries are lower than in industry, plus research only pays a part of their salary, just summer support. Moreover, students get much lower salaries than people in industry. The industry overhead, which is typically 100%, is roughly double what the overhead is for universities, since they have more layers of management at companies. This lower cost means that government-funded academic research can go much farther than for the same investment. Let me, at the end here, summarize my top 10 reasons. This is built on the 1945 paper from Vannevar Bush, and looking at it 80 years later of his remarkable suggestion and prediction. And if you're interested, you can go to that paper when it appears in Communications WCM. Thank you for your time.
Thank you, David. Thank you very much. We start with Vannevar Bush and we end with Vannevar Bush. Julissa, any final comments then from the chat? At some point, we have more than 200 people on YouTube, but for some reason, they do not post many comments, because on YouTube, if you have to post a comment, you have to subscribe to the channel, and probably that's one of the reasons. Julissa, any comments there?
There was too many comments on YouTube. However, I have been monitoring the Q&A on Zoom, and I'll speak on behalf of a couple people, but this was an excellent webinar. As a scientist myself, I can say I feel a lot more informed and know what I would have to do, obviously, to be a leader in science. Thank you for organizing this, Walter, and thank you to the panelists for taking the time to share their perspectives, because now I feel mind-opening.
Thank you very much, and thank you for volunteering to be with us today. She took my class in biochemistry last winter, and when she saw the announcement of the seminar, she volunteered to help, and it was a very helpful to have you here. Thank you very much. So Brand is still here, Sujay, John Hildebrand, Claudia Polsky, Marcia Makinat. The other panelists had already to leave. Thank you so much. Thank you everyone for your participation. I'm so sorry that we could not have time to answer all the questions. I'm already running this meeting here on a Brazilian clock. It's going half an hour behind the schedule. So, but there were so many good contributions that I could not overlook. I had to share with you all. Thank you so much. When the video is ready, everyone who signed up for register for the Zoom call is going to receive a link. And I'm going to encourage that people send a summary of the discussion here to the lawmakers. I myself am going to do that. And I want to disclose that when the discussion started, I contacted the office of Alex Padilla, one of the senators from the state of California. She was inclined to attend, but as you know, the voting went on, and no senator was available at this point. So thank you all. Thank you very much. And let's continue this conversation, and let's defend science, because it's important for everyone, not only for us.
Thank you, Walter.
Thank you, Brandy.